Look at your hands, the device you're holding, and the room around you. Exactly 13.8 billion years ago, every single atom that makes up your reality was compressed into a space smaller than a single microscopic particle. And then, in a fraction of a second, it began to grow. It is a difficult concept to accept because of what we see when we step outside. If you look up at the night sky, it feels completely still. The stars appear fixed, locked in a quiet darkness that seems to have always existed. In the 1920s, an astronomer named Edwin Hubble shifted the study of the cosmos from theoretical models to direct evidence. He spent his nights staring through a massive telescope at distant galaxies, looking for physical proof of how the universe behaves. This chart visualizes Hubble's defining discovery. He plotted the distance of these galaxies against their velocity, and the data formed a clear, upward trend. Almost every galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. If you apply basic physics to that movement and run the clock backward, the implications are clear. If the cosmic debris is flying apart today, then all matter must have been physically closer together in the past. Rewind the tape far enough, and every point of light collapses back to a single hyperdense origin. Hubble's data replaced the idea of an eternal static universe with a dynamic one. The cosmos is actively expanding, which requires a specific, measurable moment when that expansion started. If the universe truly erupted from a dense, unimaginably hot point, theoretical physicists realized there should be physical evidence left behind. The modern sky would still be flooded with the residual heat and radiation from that initial outward push. In the 1960s, Arno Penzias and Robert Wilson were operating a massive, highly sensitive radio antenna in New Jersey. But instead of getting clean data, they were plagued by a persistent, annoying microwave static they simply could not eliminate. They checked their wiring and even crawled inside the horn to scrape out pigeon droppings, assuming the birds were causing a hardware malfunction. Yet the hiss remained. More importantly, it hit the antenna uniformly from every single direction they pointed it. What their antenna was picking up was the cosmic microwave background. They were listening to the very first light allowed to travel across space, released roughly 380,000 years after the expansion began, when the early, chaotic fog finally cooled enough to let radiation travel freely. This background hum was the physical echo of the beginning. By detecting the leftover heat that theorists had predicted, Penzias and Wilson provided the hard physical proof needed to validate the Big Bang Theory, earning them the Nobel Prize. To understand exactly what produced that light, we have to rewind to the moment of the singularity. There was no explosion into a pre-existing void. Space and time themselves began with this event. It is the point where the coordinate system of our universe starts at zero. In the smallest conceivable fraction of a second, the universe underwent cosmic inflation. Space itself stretched outward in every direction simultaneously, expanding at a rate faster than the speed of light. The immediate result was a roaring furnace. With internal temperatures at trillions of degrees, it was far too hot for any solid structures to exist. Only a chaotic, glowing ocean of pure, dense energy could survive. But as the physical volume of space expanded, the temperature began to drop. As it cooled, that raw energy slowed and settled, binding together to form the first stable atoms of hydrogen and helium. Within just a few minutes, the universe had manufactured the raw chemical ingredients that would eventually ignite to form every star currently burning in the night sky. This creates a gap in the timeline. The early universe was almost entirely hydrogen and helium, yet you cannot build a rocky planet or a complex biological organism out of just two light gases. This graphic breaks down the chemical composition needed to construct a human body. We require a specific mix of heavy elements: oxygen for our lungs, carbon for our cells, calcium for our bones, and iron to carry our blood. None of these materials were present in the immediate aftermath of the expansion. To create them, the universe required billions of years and the crushing internal gravity of massive star cores to violently smash simple particles together until they fused into heavier elements. When those massive stars finally exhausted their internal fuel, they collapsed and died in spectacular explosions known as supernovae. These violent events blasted their newly forged iron, carbon, and oxygen outward, scattering a rich dust across space. Over immense stretches of time, Gravity pulled those clouds of heavy debris back together. They accreted and stabilized, forming rocky planets with solid crusts, pooling into liquid oceans, and eventually assembling into biological life. As the astronomer Carl Sagan observed, we are made of star stuff. Every atom inside your body was manufactured in the furnace of a dying star, billions of years before the Earth even existed. The chain of events starting 13.8 billion years ago produced the specific chemistry required for biological life. You are the universe looking back at itself, finally able to see the process that brought you here.